Hello. So we are doing today the Leetcode problem 325 called maximum size subarray sum equals k. And so the problem states that given an array names and a target value k, we want to find the maximum length of a subarray that sums to k. So we want to find the maximum length of a subarray in this array such that the sum of that subarray is k. If we find one such subarray, we need to return its length. Otherwise, we need to return 0. And so, okay, they are guaranteeing that it's going to be 32-bit signed integer. And then here's the example. We have this array here. We need to find the subarray that sums to 3. So remember, subarray means it's contiguous. And so an element that the longest one that we can find in this array is this portion right here. So 1 minus 1 is 0, plus 5. So 1 plus minus 1 is 0, plus 5, that's 5, plus minus 2, that's 3, which is equal to k. And so this is the longest, so we return its length. Same thing with the other examples. And the solution asks us to do it in open time. So when I was solving this problem, I tried first a solution that turned out to be oven squared, that got time limited exception on like this case number 30 out of 35. So I'm just going to skip to that solution and go right away to the oven solution. So let's see how we can do this. So let's take first the array that we have. So the way we are going to solve this is we are going to take, so there is an interesting intuition that can, once you realize it, you can solve the problem. So if you have a sum of some range that is ending at I1, so sum that is ending at I1, or I2, let's say, and then you have another sum that is ending at an index before that. So let's say that is sum ending at I1, and you have that equal to k. What does this mean? That means that between I2 and I1, in this range basically, that those elements, their sum is equal to k. And so this here, what does this here mean? That means we can just keep accumulating the element of the array, right? And then have a map that kind of takes the current accumulator value and maps it to the index at which it ends. So each accumulator value is kind of represent the sum ending at index I. So so the key in the map here, so key represents sum ending at I, right? And so every time we get a new sum ending at some index I2, we need to check if we can find another sum in the map that we already put, such that we get this here, so that we can know that we found the solution. And so how would this, so once we find that, if we find the one that is there, then we can just return I2 minus, actually we can just return so the key represents the sum ending at I. And so if we find we find this, that means we just need to return minus k, all right, as the length. Actually, this is wrong. Okay, let me do this step by step first. So if we put the key here representing the sum ending at I, and we have the accumulator, which is kind of represent here this sum I minus 2. And so let me just write it here. So we have accumulator minus the previous sum that we encountered, right? is equal to k. So this basically is equivalent to the fact that accumulator minus k is equal to some previous sum that we already found, right? And so if we in the map we record the key and where that sum ended, if we do map of accumulator minus k, we will get the index at which this sum ended, which is I1, right? Now, if we have I1, then since the range is I1 to I2, so to find the length, we can just, so the length of the sum that is equal to k, that's just going to be I2 minus accumulator, minus the map of accumulator minus k, right? That's the length, basically. So this here is, remember, this here is just I1, right? Which is I2 minus this, right? So essentially what we are doing is we are going to keep an accumulator, and every time we encounter a new I, we store in the map the sum ending at that I. And so we store, so first we store for this array here, what's going to happen is that our map is going to store first 1, which is the sum ending at index 0. So this one is sum ending at index 0. And where it ended is at index 0, right? And then for minus 1, which is minus 1 plus 1, that's 0. So this is sum ending at 1. And then 5 plus, this whole sum here is 5, which is ending at index 2. And minus 2, so 3 is this whole sum here, which is ending at index 3. And this entire thing is 5 ending at index 4, right? So now every time, how can we find the range here, which is this? So you can see that here we have so what we want to find is every time we subtract from the accumulator so far, we subtract 3 to see if that sum is encountered before. So at 3 here, if we subtract k, which is equal to 3, we get 0, right? So here, 3 minus k is equal to 0. Let's go step by step. So here, 3 minus 0 minus, so 0 minus k is equal to minus 3. That's not in the map, so we can skip. Not in map yet. So we can just continue. Here, it's 5 minus k. So here it's 5 minus k, which is 2. So that's also not in the map. So we continue. Here it's in map, so it's here. So here we have a possible result. And so what is that possible result? So the accumulator is currently 3. So 3. So what we want basically is this formula here, right? I2 is the current index. So that's basically the current index at here is 3. And the map of accumulator minus k, which is the map of 0, that's 1, right? So minus 1. But we have a problem since this gives us 2. So what we want here in order to prevent this problem is to initialize to 0 minus 1 to account for the 0-based index. And also what we want, this is a little bit of example, is a complicated example, sorry about that. But so if we do this, then we will, instead of doing minus 1, we would do minus minus 1. which will give us 4, which is the result we are looking for. So this is basically the logic is accumulate and then try to find, when you find the sum that is ending at some index I, and then when we subtract k, we find a sum that we already encountered before, then that means that between that previous index and this new index, we have a range that sums to k. And so we just need to calculate that range. And the way we calculate it is by taking the current index minus the previous index of that sum that we encountered before. That's the main idea. And so let's try to code this up. And so the way to code this up is we need a map, and then we need an accumulator, and we need the final result. And so we said the map will just initialize 0 to -1 for the counting, because basically if we are here and we say 0, 1, 2, 3, 4, and the sum starts here, say for some value of k. If we do 4 minus 0, then we get the length is 4. That's not what we want. What we want is 5. There are 5 elements. So to just account for that, we initialize 0 to -1 so that the counting adapts to the zero-based indexing we are doing here. Yeah, that's the gist of it. And the accumulator is 0, the result is 0. And so we go through our array, our list here. And then we just put the value in our accumulator, and we check if the accumulator is not yet added to the map. We are going to add it. And remember what we said here, we are putting the index that the sum ended at, which is this I here. And then we are going to check if we had a previous sum that is equal to the current sum minus k, which means that the interval between those two sums to k. So if we found such a sum, then res basically is the max of what we said here, right? So res and this is I, and this is what we have, same value here. And then we can just return res. Okay, so let's run this here and see. Oh, it's M actually, yeah. Okay, let's take this other example. Good. Let's take one that is a little bit of an edge case. Good. Let's take with an empty list. Good. I think we can submit this. Okay, so it passed, and that's the solution here. Yeah, so basically this idea of the accumulator here and also finding a previous sum that exists already in the map is a pretty clever one here. That's about it. Thanks. See you next time.